Our job in physics is to see things simply, to understand a great many complicated phenomena in terms of the few simple principles. Steven Weinberg, Nobel Prize Lecturer, 1979. Murray Gell-Mann and George Zweig introduced the idea of quarks into the physics literature in 1964. It was an elegant idea. It certainly helped describe and explain a lot of data, but it was quite controversial and subject to a lot of debate and analysis for many years, in part because it was just a model. It was just a clever but crude collection of ideas, which made some sense of a lot of data without deeply explaining it. And I think a crude, quantitatively successful, sometimes quantitatively successful model and I think a crude, qualitatively successful, sometimes quantitatively successful model is good enough in a lot of branches of the science. But particle physics is beginning to expect a little bit more. I think already by the 1960s there is a sense that we should really be able to make concrete and deeply rigorous statements about how the world works. It's kind of the philosophical attitude, a belief that the world really is simple, and that simplicity can be described and explained mathematically. And so this is now the goal, I think, of particle physics, starting from the introduction of quarks, to come up with not a model, but a theory, a mathematical framework in which one could calculate and predict any observable that you could ask for involving subatomic particles. Now, we already had a framework, a mathematical theory, which was very successful for describing electrical forces, and that's the quantum electrodynamics. Quantum electrodynamics is a theory. You can write it down on a piece of paper. It's a got particle constituents. It is a got particle constituent, that is to say, electrons and any charged particles, and it's got formulas which tells you how to make quantitative predictions about the behavior of those electrons in the presence of other electrical charges. It includes the effect of the vacuum fluctuations, virtual particles spreading out of the nowhere and then re-annihilating very, very quickly, which make tiny but sometimes important modifications. So that's kind of the template that the physicists are looking at and wondering, can we make a quantum field theory for the strong force? Now the particles that are going to go into your quantum field theory will be the quarks. This is the idea, because we are looking for strong forces. The electron has nothing to do with the strong forces. The electron isn't made of the quarks. It's got nothing to do with quarks. It's a whole separate story by itself. We are focusing on the hadrons and their constituents now. In the theory of quantum electrodynamics, there is a very, very important quality. Very, very important quantity that every particle possesses, and that's the electric charge. It's a number. The electron has negative 1 in a certain unit system, the proton positive 1, and so on. Every particle has a certain amount of charge. Charge is absolutely essential in quantum electrodynamics because it tells you the strength of interaction, The electrical interaction depends on your electric charge. The more charge you have, the stronger the interaction. It's really the key ingredient. It's not the electron, it's the charge on the electron that's really essential. Unfortunately, we don't know the analog for the strong or nuclear force. We know that quarks carry something, but what do they carry? They do have electric charge, and so they are going to have electrical interactions. But electrical interaction don't explain why the quarks bind together. In fact, electricity would make them want to fly apart. Two up quarks, for example, have the same charge. Electricity makes them want to fly apart, but they can be bound together in a proton along with down quark. You need some much stronger force to overwhelm the electricity and bind them together. Yes. There was some evidence and more theoretical arguments which had developed in the 60s, which pointed to a new quantity of nature which would play the role of electrical charge. It would be like a strong charge, and it took a long time for this story to develop. It took about 10 years for people to really put it all together into the formal theory. And the formal theory that developed was even more complicated than quantum electrodynamics in a lot of ways. We are not going to go into the mathematical details, but again, I think the essence is something that is very much graspable. So, what is the extra thing that people are looking for? Well, let me tell you about a puzzle that led to a sort of idea which led to the idea of what the electric charge is. It was a chain of the logic. Think about the delta particle. I've never really said much about it except that the delta particle is kind of the heavy version of the proton. It decays strongly and rapidly and turns into the proton. In the quark model, the delta is an up and an up and an up, and the delta particle has a spin 3 halves. So it must be an up quark which is spinning clockwise, and another which is clockwise, and another which is clockwise. That's what delta particle is. It's just this little combination of the 3 identical up quarks spinning all the same way. Yes. Now, if you are a quantum physicist, you say, hold on a second, no way. Because an up quark has a spin 1 half, you can't put 2 up quarks into the same quantum state. Yes, you can't put 2 up quarks together. You certainly can't put 3 together if you can't even get 2 of them together. So there is a dilemma here, and there is only one way out of this dilemma in the quantum mechanics, and that is you are allowed to put the particles together in the quantum mechanics if they are distinguishable, if there is something different about them. So it's no problem to put an up and down and strange together, and it's even possible to put an up and down together, as long as some of them are spinning clockwise and some of them are spinning counterclockwise. But how on earth can you put 3 up quarks together? The answer would have to be that there is some other property of the quarks. They contain some other information that we haven't thought about it yet. It would be a new quantum number, and apparently there have to be 3 different possible values, not just 2. It can't be like spin, where you can be clockwise or counterclockwise. You need a new variable that has 3 degrees of freedom instead of the 2. What shall we call this? A new degree of freedom? People had a clever idea. Let's call it a color. Yes. So we could have a blue quark and a green quark and a red quark. Yes. And now they are distinguishable and they can go in the same place. Now please bear in mind, it's not really blue. It's not going to do with the color that you see with your eyeballs. That color, the blue that you see with your eyes, represents very long wavelengths electromagnetic radiation. It's just a metaphor. Red, green, and blue are 3 colors in the color wheel, and just a nice way of representing different properties of these quarks. Yes. So, if the quarks possesses that we now call the color, which again is this physics word that doesn't mean visible color, then we can explain how it is that you can put 3 what look like identical quarks together and form a delta particle. And there were other various pieces of evidence that color was, in fact, a degree of freedom. sometimes you can do experiments bouncing off quarks where where you can count how many different quantum mechanical degree of freedom they have, and the answer seems to be 3 rather than the 1. So people got the clever idea that this new property of the quarks might also be a charge of the quarks that's responsible for them binding together. So they called it a color change. And the color force is the force that arises when you got a color charge near each other, right? And this turned out to be a brilliant idea, and it is a basis for theory that we now have, which explains in a great detail the interaction of the quarks. Right! Now, one of the big puzzles of the day is why do the quarks combine it in threes to make baryons? If you think of a color wheel, the metaphor gets better and better. On a color wheel, there are 3 primary colors, only 3, exactly 3. And if you add the 3 primary colors together, you get white, which in a certain sense you could say is colorless, or you could say it's all colors. But in any case, it's a sort of a neutral color, and so supposing you look at 3 quarks, red, green, and blue, if you combine 3 quarks together and they form white, then you have no net color left. Yes, and so a white object and another white object will not attract one another particularly strongly. Wow, what an analogy! So great about 3 colors. And that's why a proton over here and a proton over there don't feel each other at all. Wow! Because they are white subjects. They don't feel this strong color force. A red quark and a blue quark, those are different colors. They feel an enormously strong force, 100 times stronger than the electrical force, which is what binds them. Aha! Now, it's not true that they feel absolutely nothing, because the red's in the one spot and the blue is slightly displaced, because these are the quarks buzzing around one another. So as 2 protons get closer and closer together, even though they are overall neutral, the fact that they have a little distribution of the color change inside of them makes them begin to attract as they get closer, which is just the way protons behave. They feel no force until they get about the femtometer apart, and then they stick very strongly, because now all of a sudden these colored quarks are right next to each other, and they notice that there is a color nearby, and everybody binds together. So this metaphor of color is a nice one to help explain the properties that had been observed already starting in the 1930s about how the strong interaction works. How about the mesons, the particles that are built not of the 3 quarks but of the quark antiquark? Well, that works too with this metaphor. If you have a color and its anti-color, that would mean straight across it on the color wheel. These also add to white, so a meson, which is a quark and the anti-quark, would be red and anti-red, for example, and those will combine together as they will attract very strongly, because they are different colors. But when you look at the 2 of them together, they form white, and so a meson, like a proton, will most of the time feel nothing until it gets really close. And then it feels a strong force of nature. This is still not a theory. What one needed to do is write down a mathematical framework that's just like a quantum electrodynamics, only instead of having 2 electric charges, you are going to have 3 color charges, and now you are going to try to kind of mimic the mathematics of quantum electrodynamics. And people came up with a clever name of the quantum chromodynamics. Chromo meaning color. Yes, chromatography. Chromo meaning color. So this is a quantum field theory of color forces. Quantum chromodynamics took a long time to develop. This is QCD, huh? In part because the mathematics of the three is a lot more complicated. Yes, three-body problem, right? It's not just a 50% more complicated. It's a lot more complicated than the mathematics of the two different charges. Of course. Let me say a word about QED. When you have a charged particle, it has an electric field around it. That's one of the way, a classical way of thinking about the force created by electricity. And what is a proton? What is a photon? How do you think visually about photon in this classical picture? Well, jiggle that charge. If you jiggle a charge, you are jiggling the electric field, and it's a jiggling electric field which propagates out like a jiggling water on a pond and make a wave that travels out. So when you jiggle an electric charge, classically, you get an electromagnetic wave. Quantum mechanically, you emit photons. So I think of photons, the particle of light, as a jiggle in the field. And so, if we have a colored object and there is a color field around it, if you are to jiggle it, that would be the way that you would propagate the strong force. And what would the particle of the strong force be? Mr. Yukawa thought it was the pions, but we don't think that anymore. The pions are themselves just a quark and anti-quark pairs. We are looking at a level deeper now, and we are saying it's a color field, and you have to give a name to this jiggle. Instead of the photon, we call it a gluon. Yes, glue. It's another one of those silly names that physicists came up with, but it's nice. It's a name for the force carrier of this strong color force of nature, and it really is like a glue. It makes things stick together incredibly strongly. Yes. If you are trying to picture a proton, you've got the three colored quarks, and the colored quarks have these color fields around them. There is a little cartoon that you can draw. This is not a physicist's diagram, it's just a sketch of the proton with a red quark and a blue quark and a green quark in it. And then these little lines going between them are supposed to represent the color field in some artistic sense. It's a gluon that are binding the quarks together, right? One of the complexities, and in fact very important aspect of this color theory, is the following. If you have an electric charge and it emits a photon, the particle, the wiggle of the field is itself electrically neutral. An electron has a charge, but the photon does not. The photon interacts with charges, but it doesn't have its own electric charge. But when you work out the mathematics with the color forces, with quantum chromodynamics, you discover that the wiggles in the color fields are themselves colored. So a gluon has a color charge on it, and now you think, oh my goodness, that means that a gluon, as it's traveling along, can interact with another gluon. Gluons can make gluons. This is a part of the reason why the strong force is so strong, so much stronger than the electric force. You start off with two color charges and they produce a color field between them, which enhances itself spontaneously. If you are thinking in terms of the Feynman diagrams, which would be the way that you would try to calculate these forces, an analogy with Feynman diagrams in QED, life becomes complicated. You draw one diagram with some gluon in it, and then you have to draw another diagram with more gluons and gluons meeting gluons and gluons forming all sort of complicated structure. And because the force is so strong, the diagram don't get smaller and smaller as you add more and more complexity. So it becomes very difficult to do numerical calculation in quantum chromodynamics. I could take a graduate student in the field theory course, so that would be maybe a second year physics graduate student, give them a homework assignment to evaluate a simple quantum electrodynamics processes, like an electron scattering of another electron, and they could do that in a week or two. But I can't do that in the quantum chromodynamics. It would be a whole thesis project, and even now, people are still today doing research trying to figure out how to mathematically compute these complex diagrams. There are many consequences, some of them can be computed. It's not that we can't do anything, it's just that you can't do everything in the quantum chromodynamics like you can in the theory of the electricity and magnetism. For example, supposing you take 2 quarks or 3 quarks, you have some object and there is all these color, the glue fields, and you start to pull apart the quarks. Now that's a sort of a metaphor. How would you really do that in the lab? You might send an electron beam in which walks into one of the quarks and sends in flying by the electrical interaction. In any case, you could imagine an experiment where you try to pull 2 quarks apart. Well, what's going to happen? As you pull, the gluonic field gets stretched. Gluons are bosons. They love to be near other gluons. So you'll start to get more and more gluons, kind of stretching in a line in between those 2 quarks. You get a very intense blob of gluons in there, and the more you stretch it, the more glue you are going to have, and the tighter it's going to pull. So it's like a rubber band. As you pull these quarks apart, there is a rubber band force of nature which is pulling them back together. So that makes you think that it's going to be really hard to get a quark out of a proton. So you sit down, you start calculating with this fielding theory of the quantum chromodynamics, and you discover, in fact, it's impossible. The more you try to pull them apart, the stronger the strong force gets. It actually grows with distance, like yes, like a spring. Unlike all the other forces we know about, like gravity or electricity, that get weaker as you get farther apart, and so there is no limit to how strong this can get. The quark is confined inside of the proton. There is no way to get it out. You could stretch it, you could add energy to the system, but you'll never get a free quark. So the theory of quantum chromodynamics is actually making a quantitative, maybe a qualitative prediction that you won't observe a free quark in the laboratory. Yes.